Okay, for this one, project number 2, I'm going to make at least 4 videos because I'm going to break up the pencil and paper part into 2 videos. In this first one, I'm going to solve for the charge that the negatively charged fixed particle has to have in order to make it so that the positively charged particle gets as far away from it as the baseball gets above the surface of the earth. And then I'll do the part 2 for the pencil, or the next one for pencil and paper will be figuring out how I got to write the code, any algebra that's got to be done for that, and also the outline of the actual program. So let's get started on finding the charge of that negatively charged particle. I'm going to go with conservation of energy. So first off, the baseball. I want to find out how high up it gets. So I'll call this my reference level. Let's try that again. Reference level y equals 0, and the baseball starts out at what I'll call y1, 15 centimeters, 0.15 meters, and it's got some velocity. It's v1 is 25 meters per second, and then in the after picture it's up high, y2 and v2 is 0. And so I'm trying to find y2. Let's make sure I got values right. 15 centimeters and 25 meters per second. Baseball times 0, 15 centimeters above the surface, and we move straight up with 25 meters per second. Okay. So E is equal to E prime, or E1 is equal to E2. I'm using 2's for after and 1's for before. So I got K plus U in the before picture is equal to K plus U in the after picture. There are 1's for the before, 2's for the after. Kinetic energy is 0 in the after picture. Relative to my reference level, it's a little bit up high in the before picture and more so in the after picture, so both U's are there, and it's moving in the before picture, so I got a K. So 1/2 mv1 squared plus mgy1 is equal to mgy2. And the m's cancel. I'm solving for y2. Divide both sides by g. It's going to be y1 plus v1 squared over 2g. So y2 is equal to 0.15 meters plus 25 meters per second quantity squared divided by 2 times 9.80 meters per second squared. Y2 is my trusty calculator. Turns out to be 32,038. It's supposed to come out in meters. It's meters plus, and then we got meters squared per second squared divided by meters per second squared. That does leave meters. Okay, so I got y2 So now what we're saying is we want the negatively charged particle to be big enough, have enough negative charge so that the positively charged particle gets that far away from it. Alright, so charged particle, new problem. So new prob the moving charged particle. So we got a fixed charge particle minus, look like it's held down by something here, and then a positively charged particle. Alright, this one has charge QF, I'll call it. This charge Q, which is equal to 567 nanocoulombs. 567 times 10 to the minus 9th coulombs, and it's got a mass of 0.25 grams. 0.25 times 10 to the minus 3 kilograms. It's moving at an initial speed, I'll call it V1, equals 25 meters per second. Just want to make sure that that's 25 meters per second, just like the baseball. Okay. And I think this is going to be an interesting comparison. So we got something moving in a uniform field, a gravitational field, experiencing a constant force, so constant acceleration, and it's got one graph of position versus time, and then we got one that's got this 1/r² force, and it'll be interesting to see how they compare. This was the before picture for the charged particle, and then in the after picture got the negatively charged particle still here. This guy much further away, not really to scale. If that was R1, 0.15 meters. This is R2. Really should just go right out to the center of the particle there. R2, which is what we found for the baseball, 32.038 meters. We want the charged particle to go as far away from the negatively charged particle as the baseball did away from the surface of the Earth. And V2 is equal to 0. I think I got enough to analyze that. Let's go ahead and say E is equal to E prime. So K plus U is equal to K plus U in the after picture. Those I'm using 1s and 2s over here. Kinetic energy in the after picture is 0, and the before picture is 1/2 m v1 squared, and it's the charge of the victim, the Q, times whatever the electric potential is at its location in space, and that's equal to Q phi 2. This would be phi 1. So let's see. I'm looking for the charge that's wrapped up in both of these phi's. I think I'll go Q times phi 2 minus phi 1 is equal to 1/2 mv1 squared. And then let's try simplifying these phi's. It's going to take me a little bit of space, so I can keep on going here. This is Q times K, Q fixed, the negatively charged particle, so that's a negative amount, divided by R2, then minus KQ fixed over R1 equal 1/2 MV1 squared. I want to make sure this is coming out right. So, because I got a bigger denominator here, magnitude-wise, this is going to be a smaller magnitude, but it's negative. Minus minus, so the big term is going to be positive. That's positive. Yep, this side's positive, so it all comes out positive. It's working. So what do I got? I got. I think I'll try moving up here now. Nice to be able to see the picture. I'm going to factor out a K and a QF. So I got K, Q, QF times 1 over R2 minus 1 over R1 equals 1/2 MV1 squared. So QF is equal to MV1 squared divided by that 2 KQ, dividing this by both sides, and then dividing both sides by this, dividing both sides by this, and then dividing both sides by that. 1 over R2 minus 1 over R1. So QF equals 0.25 times 10 to the minus 3 kilograms times 25 meters per second squared, all divided by 2 times 8.99 times 10 to the 9th Newton meters squared per kilogram squared times Q. Oh, wait a second, I'll need some parentheses there. Times Q, which, here it is, 567 times 10 to the minus 9th. Coulombs. And then, times 1 over R2, which is 32.038 meters minus 0.15 meters, 15 centimeters. Alrighty, what does that give me? Q sub C equals, okay, I'm just going to plug those into the calculator. And of course this is 1 over that. I'm getting minus 2.3098 times 10 to the minus 6 coulombs. So that actually represents the charge of the negatively charged particle. I'm going to check that real quick, and I'm getting the same thing again. Let's make sure the units work out. I got kilogram meters per second squared times meters. That's a Newton meter. So I got, yeah, the units aren't quite working out for me. Newton meter squared per coulomb squared. I got a mistake in there, so let's go with see if I can fix that. I got the units of K wrong. It's Newton meter squared per coulomb squared. So the units were not working out for me. But let's see if they do now. So this is a kilogram meter squared per second squared. That's a Newton meter. So that'll get rid of a Newton meter there. And we're left with just 1 meter in the denominator. And then a meter divided by coulomb squared. And so I got meters divided by 1 over coulombs, so meters times coulombs, and then nope, it's meters per coulomb in the denominator, so it's a coulomb per meter. Meters, a meter was left and a coulomb's left. A meter per coulomb in the denominator, so a coulomb per meter, and then times, and this is a meter, so that does wind up with coulombs. So 1 over meters in the denominator, and then I take the reciprocal of that, I get meters, and so that cancels out the meters and the coulombs per meter, so I'm just left with coulombs. It's negative, which is what I was expecting, so the things that I can check obviously and quickly work out. If I got some number typed in there wrong, hopefully I'll find that before the end of the final video. Make sure you look at all the videos in case I got some mistake that I come back and fix. Alright, or a student points out to me an error and I fix it. So that does it for, I'm going to call it project number 2, video 1 of 4. It's part A of the pencil and paper part. I got another part, I'll call it part B of the pencil and paper part to do.